Hello, and welcome to the third training series on using vectorsurv data in R. This training is going to focus on our calculator functions. And if you have not seen the previous two videos, I highly recommend watching those now. The link to those videos is in the description. As well, the guide that I am using today is also available for download. So as noted, this session is covering the calculator functions. We have a couple calculator functions in this package. They all follow very similar to those that we use in our gateway. So if you are not familiar with the calculators, please check them out on the gateway. Today I'm going to give an overview of what the calculators are doing and how to run them in R. So let's go ahead and install our package. I have already installed mine. Please reinstall the R package if you've not done so recently. We do release updates routinely, and I'm going to skip that step because it does take a bit of time. Right here, I'm going to load, and then check your package version. You should be running 1.51 for this training. All right. So we covered how to retrieve data using our API in R. Right now, this training does not need to use our agency data. It can use the sample data that is available for all people who have downloaded the R package. I did provide a quick recap on how to get your collections and pools data using our API. However, I commented it out because I'm not using this for the training. I am going to be using our sample collections. And so you should be able to just run sample collection and it will appear. This is sample data. The agency is agency. It is not real data. It is meant to mimic actual data and it can be used with our calculators and any of our functions in this package. So I'm going to set my collections and pools to sample pools and sample collections. If you would like, you can continue this training using your own data. You would have to then get that here. So we have 4 calculator functions to cover. They all share a couple similarities. So they all are going to require an interval. The interval is a time interval, and it can be in collection date, week, bi-week, or month. They all also require a data source, and that's the collections or the pools data, and sometimes both. Now there are some optional aspects to all the calculators as well. You can filter on the actual calculation. You can filter by agency, species, trap night restriction, sex, etc. And you can group or otherwise known as separate by the calculation out. And so you can separate by additional variables such as agency, species, trap, county, and spatial features. So here I have provided the formula of the abundance calculator. Now the get abundance calculator is going to calculate mosquito abundance on a time interval, year, and other optional variable. So this is going to be the standard abundance here, where it's just calculating the total number of individuals. This is unfiltered, divided by the total number of trapping opportunities for that time interval and year. So we can also pull up the documentation for all of the calculator functions by running a question mark in front of our function. So here I'm going to run get abundance. It is control enter to run a single line in R. So I run that, and we can look at our documentation and see that we do have some defaults. For one, sex is defaulted to being female, trap night minimum is defaulted to being 1, and then a couple are defaulted to null, meaning that there's no filter in place. I'm going to run the weekly abundance, take a look at it, and give you guys a rundown of what's going on here. So this is just the top portion of the weekly abundance result. This is for our sample data, obviously. And so as you can see, it's by year, and then we have our species, count, trap events, trap, and abundance. This here species is giving a breakdown of the species that are present in this calculation. For this week, we have these species available that were found and used in the calculation. Now the next week, we see that there is one less, and in the following week, there's quite a few more. And this is just giving general breakdown of the composition of the data that is being used to calculate this abundance. The same thing is shown for trap and other variables. So you might not want to include everything in your calculation, and from that we can filter. And so we can filter directly in our function. I recommend filtering directly in functions because it avoids confusion and potentially having issues where you might accidentally filter on one data frame and not realize that you filtered on a certain species, and that can definitely change the output calculation and what you're looking at as a result. So in our documentation, these agency, species, trap, sex, these are all filterable values, also trap night, and so on. So let's start with species. And so as you can see here, you can see a list of what you can input as a species by running the unique collection species display name, because this is taking directly from our species display name column. And so this will give you, just allow you to know what you can actually input as your species. And so here we're going to choose Pipiens and Tarsalis. I also choose trap of BG Sentinel, and note that trap is trap acronym, so you can run that as well to see what traps you have available in your data. So you can run that, and you can see that this has now been filtered accordingly and only includes these species and this trap. Now, an important thing to point out is when you are filtering by multiple species, you need to input these character values into a vector. So a vector here is denoted with the C. If you do not include the C and you just list out multiple, you will get an error. It will not run. And of course, you don't have to put multiple. You can just put a single one and run it that way. And so right here, I added an additional trap. And of course, every time you filter, it will change your calculation. So if you are going to be using this in a project or a report, it's a good idea to label this a little more consistently so that you know exactly what's going on. You can now group the calculation as well. So here's the formula with a grouping. It just adds an additional layer to the data, and that is the grouping layer. So on top of being with interval and in the Z's year, it's also going to be calculating by that group. The group here can be inputted with the separate by parameter. So here we have the separate out by species. And if we look at that, we'll notice that now there is going to be an independent row for each species for each week and each year. This does increase your data's dimensionality, which can come into play when you are graphing. If you have data that has too many dimensions, it might look strange when you're graphing by week because you may end up with multiple values appearing for 1 week if that's your time interval. And so you may need to filter if you're going to graph this appropriately or do different graphing methods. So here we'd have it by species and trap. And so this adds a whole nother row here just for trap as well as species. And so this can get complicated if you aren't careful in how you're organizing your data. Okay, moving on to the Get Abundance Anomaly Calculator. Now this is going to compare a target year's abundance against the multi-year average for the selected groupings and filters. I'm just going to provide the ungrouped version for the rest of these calculators because it's pretty much just adding another variable on. And so this right here, let me actually show you guys the Get Abundance Anomaly documentation so you guys can have a little bit of a better idea of what this delta means. So it looks very similar to our Get Abundance. However, we are requiring a target year, and it is ideal to have a target year that is the most recent year in your data if you're going to retrieve data. So here, if I do target year is 20, okay, also one thing we can do is we can actually look at how many years we have in our data. Including collections, and then surveillance here. And so as you can see, this is the years in my sample data. I'm going to choose 2020, and I get a little warning that tells me that there's a year additional in my data, but that's okay. It's just a better idea to have more recent years and more data. The more data, the better for this calculator, or else it's just going to calculate as many as it can. However, we can help it do its best by providing it with adequate data. So here I chose 2020. This is going to, and I chose month. And so it gives a similar breakdown as get abundance, except now it calculates the abundance of that year, and then it's going to calculate the 5-year average. It will give us the years that were used to calculate that average and this delta value. Now this delta value is the anomaly value, and that is calculated as the difference between the current year's abundance minus the overall abundance for that interval divided by that overall abundance. And so here we see that delta is negative. This is because our abundance is less than the 5-year average. And this is used more in graphing, but we'll get into that in the next training. Just like in get abundance, we can filter, we can separate, we can get all kinds of different things and break down the calculation however we see fit. Now, you can run into an issue where you are missing data, and so you can get some strange values. It's always a good idea to keep an idea of what kind of data we're putting in to get something that's more realistic. Obviously, this delta value is insane. It's comparing two single instances of collections where one is very big and one is very small. I left this in here intentionally to point this out. As you can see, when we have more data, we have a bit more reasonable delta value. Because again, like we're comparing to a single year in the past, which is likely 1 or 2 collections for this month versus many. And the more data you have, the better this calculator is going to work. Moving on to our infection rate calculator. So this infection rate calculator is giving us an estimate. This is denoted by this little caret on top. Here I've just provided a couple of different calculations for the different ways we fit this model, or estimating the infection rate because we are using a pooled data source. And so you have a pool size of 20 and a positive pool, as many of you know. Anywhere between 1 and 20 mosquitoes can be tested positive for that disease. We don't actually know how many mosquitoes are infected. We have to use statistics to get our best estimate. We pull up our documentation here. And so that's why it is a point estimate that we are looking at when we do this sort of calculation. Our point estimate is how we are going to calculate this. And 3 available ways to do this. We recommend using bias-corrected MLE. It is the most reasonable, especially if you have small sample sizes. But a very common one is the MIR, which is the minimum infection rate. MIR just assumes that 1 mosquito is positive for every positive pool. Like at most is 1 mosquito. So it's just the total positive pools over the total pools for, again, I intervals and Y disease years. And now this can also be grouped and it can be filtered within the function. So the MLE, now fitting it to a pooled binomial model, and that is how we're getting our estimate. It's based on the size of our data. And now the bias-corrected MLE is also going to be using the same similar thing. It's fitting a pooled binomial data. It's going to estimate the bias from our data of our infection rate. It's going to subtract that from our MLE estimate. Also important to note that we are multiplying this value by a scale of 1,000, and you can change the scale if you wish. So let's calculate that and get a look at it. Also, a required portion of this calculator is the target disease. This is going to be the disease acronym value, and so it is West Nile virus, SLEEV, etc. And so just keep that in mind. I put it as West Nile because that's the most I have in this data currently. And so, similar to get abundance, it's going to calculate it by the year and the interval that we have chosen. I chose bi-week. It gives you the species and the trap breakdown, and it's going to tell you your infection rate. And so it's also going to give us these confidence intervals, and the confidence intervals are giving us the confidence that we have that our true value, our true infection rate, which we don't know, actually resides within these intervals. So we're ideally, the more narrow a confidence interval, the better. Now here, as you can see, again, the confidence interval is wider, so maybe it's a little less of a good estimate, smaller, a little better of an estimate, etc. So something I do want to point out that can happen is you might end up with an infection rate that is NA or NAN, and it's not because you're missing data. You will get a warning in the calculator. I tried to recreate this on here, but I set it up so that I wouldn't have that issue. Sometimes that can happen if your interval is too narrow, or you are filtering on multiple species and separating by multiple variables, and you get this sort of NA issue. And what ends up happening is it can't estimate a situation where we have only positives in our pools, because that would be an infection rate of 100%. And that's not something that's statistically sound. You can't have an infection rate estimate of 100%. And so it will cause an error, and you might end up with an NAN. So that's going to be up to the agency to decide if they want to keep those values or what they want to do with them. But I'm just pointing that out, that might happen. So it's nothing to worry about. It's just how the data works sometimes. Okay, so we can also estimate by the MIR, minimum infection rates. Obviously, the values are going to be a bit different. Oh yes, and to note, we can separate and we can filter how we want. So here I separated out and I just did a bit more narrow, wider, etc. MLE. And we do recommend bias corrected MLE. That is the default, but you can do whatever you wish. Alright, and so our final calculator is going to be our vector index calculator. This is going to combine the infection rate and the abundance result. And so here is where it's really important not to pre-filter your data. If you pre-filter, you might end up with a collections data frame that doesn't contain a species that the pool's data does contain. And so that can cause all kinds of issues and inconsistencies. And so it's just a good idea to keep the data unfiltered and then filter it within this function. And so this is going to be the product of our abundance and our estimated infection rate for our given intervals and groupings. So we pull up our documentation, we see that it includes both a collections and a pool data frame, an interval, a target disease, a point estimate, and a scale. And it's just going to also have these filters in place. And so run that. And I guess once again, it's going to give you all the species that are available. So you might end up with a pools that doesn't have, like you might end up with situations where you did not actually put any traps out for, or you didn't test for any pools that interval, so you just have the abundance available. Sometimes you will have both available and it will all work out and you will get your vector index. However, there are times where there's missing data or instances where you get this NA. It doesn't mean that the vector index is 0, it just means that there was no data. And so, like before, we can separate, we can filter, we can do all kinds of things to get our calculation as custom as we hope. And again, as you filter and change your layers of data, you might end up with even less data available. So you can see there's a lot of NAs here. That's just because there is no infection rate data for this month time period for these specific species and these specific traps. And so as you narrow it down, you might end up with things that are a bit harder to interpret. But sometimes maybe you find just the species that's very abundant. Like this, for example, Pipiens is very abundant in this sort of data, so you might just want to filter out by Pipiens and look at that data in particular because it might be a problem source. And so that is the conclusion of our training today. Hope this was helpful. Next, we are going to look at how to graph these outputs using ggplot2. We are also looking at in the video after that, we will look at how to use spatial data, how to overlay spatial data and group by spatial features. And finally, we will review how to build automated surveillance reports and have a bit of a simple one. So yes, the next session is looking at visualizing calculators, interpreting calculators from these results. Have a wonderful rest of your day, and I hope this was helpful. Bye-bye.